Hello, everybody. Welcome back. Today we're going to be looking at Unit 9.5, which links the topics of free energy and equilibrium together. So let's get started. All right, so let's just review for a moment what values of Gibbs free energy, delta G, what they indicate. Remember that if a delta G value comes out to be negative, that indicates that whatever process we're talking about is thermodynamically favored. If delta G comes out to be positive, it is not favored. And all of the delta G's that we have looked at thus far have had this little degree symbol next to them, which indicates standard state conditions, which means 25 degrees, gases are at 1 atmosphere of pressure, and anything aqueous is at a standard concentration of 1 molar. But does that mean that we cannot predict favorability if we're not at standard conditions? And the answer is we can still make those predictions. It's just a little bit different. So there is an equation here that is not on your equation sheet. It really doesn't need to be, okay? It's called the Nernst equation. It used to be on the AP exam, at least the math associated, and the math is no longer on the AP exam. You could certainly still use this equation as, evidence to back up a claim. But what I want to highlight for you is these two different delta G's. You'll notice that one of them has that little degree symbol, which indicates a delta G measured at standard state conditions, but the other one doesn't. And so what the Nernst equation allows us to do is to solve for this delta G, meaning Gibbs free energy, but at non-standard conditions, and then the process is the same. If that delta G is negative, then it's favored. If it's positive, it's not. And we're not going to do any calculations with this. As I said, the calculations are not on the AP exam, but the concept is, okay? And that capital Q there that is in that equation is something we've seen before. It's called the reaction quotient, which, if you will recall, is set up the exact same way as the equilibrium constant K, the difference being the molarities or partial pressures that you would plug in would not be at equilibrium. Okay, and we're going to talk a little bit about what happens when you are at equilibrium. We'll get there. So if the calculations are not on the AP exam, what kinds of questions could be? Okay, well, they might look like this. Okay, the question, we're given a balanced equation, and it says indicate whether delta G, please notice that delta G does not have the degree symbol, okay, so non-standard. Indicate whether delta G increases, decreases, or does not change when the following changes are made to the reaction above. And this is a little bit of a hint. Think Le Chatelier's principle. Before we get into this, let me sort of rephrase something I just said a moment ago. When delta G is negative, we say that whatever process we're looking at is thermodynamically favored. Well, let's be more specific. If delta G is negative, that means that the reaction we're looking at, are you listening? In the forward direction is favored. Like when we say delta G negative, it's favored. The it in that statement means the forward reaction is favored. Okay. So let's look at these. Okay. First one says we are going to add more carbon monoxide gas, which is a reactant. First thing I want you to think about is what kind of a shift is that going to cause? Adding more reactant is going to drive the reaction in the forward direction. Okay, and if you think about it, this change right here, this stress that we have put on the system, has caused this reaction to shift in the forward direction. Well, that means the forward direction is becoming even more favored than it was before. So what kinds of delta G's mean even more favored? How about delta G's that become even more negative? So if we were to add more carbon monoxide gas, delta G is going to decrease, because guys, a decreasing delta G means a reaction that is becoming more favored in the forward direction. Okay, let's do another one. This time we're going to remove something. We're going to take out some hydrogen gas, which is a reactant. What kind of a shift is that going to cause? That's going to push the reaction to shift in the reverse direction. So let me ask you this. What is happening by having this stress on the system? What is happening to the favorability of the forward reaction? The forward reaction is not getting more favored, it's getting worse. So what kind of a delta G shows a reaction that is getting less favored in the forward direction? A delta G that is increasing. Remember, keep thinking, a negative delta G means favored, a positive delta G means not favored in the forward direction. Okay, third one. Pressure is increased. Okay, well, let's review way back when we learned about Le Chatelier's principle. Actually, it wasn't that long ago, but pressure is increased. What happens when you increase pressure? A reaction will move to the side with fewer moles of gas. Well, this side has 3 moles of gas. This side has 0 moles of gas. So this is going to cause a shift in the forward direction, making the forward direction more favored, more negative. Okay. What if we change the temperature? And remember, you have to, in order to predict a shift when temperature is the stress, you have to know the overall change in enthalpy. So let's review. What does this mean to us? It's a negative value, exothermic. Heat is produced, evolved, given off, more like a product. So if we increase temperature, that's like adding more heat. That's going to cause a shift in the reverse direction. That means our forward direction is becoming less favored. Delta G must be increasing. Okay, last one. This time, this compound that's called methanol. Methanol is going to be added. Be very careful. Ladies and gentlemen, there will be no change. When you make changes to a liquid, remember, changes in a liquid or a solid have no effect on the position of equilibrium. So nothing's going to change here. Okay, so you're not being asked to calculate these new delta G's when these stresses have been made. That's not on the AP exam anymore, but you may be asked to predict about the favorability of the forward reaction. Okay, now, this is something we have mentioned before. couple of subunits back. If delta G is negative, the reaction is favored. If it's positive, it's not. If delta G is equal to 0, then this reaction is at equilibrium. Well, if we look at this equation, which you don't even need to write down if you want, but just mathematically, if you set non-standard delta G equal to 0 and rearrange the equation, you get that. Now, wait a second. How come Q just spontaneously morphed into K? Well, look at the top statement there. It says that we are at equilibrium. So we don't need to use Q anymore. We can use K because we're at equilibrium. And if you will look at your equation sheet, ladies and gentlemen, this equation is right there. Okay, we now have a few ways, a few different equations to calculate delta G. We've got delta G being calculated with products minus reactants. We've got it, we learned a couple units back, delta H minus T delta S. And then now we have this new one that involves the equilibrium constant. So let's put it to use. So if you've now got something, an equation that links thermodynamic variables with equilibrium variables, wow, think of the possibilities that we could do with a free response question and link these two major concepts, but we'll get there. All right, let's look at this practice problem together. We have a balanced equation. It says, using the chart below, calculate the equilibrium concentration of carbon dioxide at 298 K. And then, guys, if you will notice, I see Gibbs free energy values of formation. And I've said this before in videos, when you see that little sub F, I want a little light to go off in your brain. This must be a products minus reactants situation, because that's when you plug in formation values. So let me get to a fresh screen here. And that's the first thing I'm going to do. I am going to calculate the change in Gibbs free energy for this reaction by using those formation values, products minus reactants. So there's the first product. Here's my second product. Products minus. Here's the Gibbs free energy formation value for my reactant. And I'm going to plug all that in, and this is what I get. And if you look at the units, guys, the table has those formation values in kilojoules per mole. That's going to be important in just a second. Okay, now, I know that I had to use that products minus reactants equation, but it also asked me something about equilibrium. So if when I look on my equation sheet, I see an equation that links these two concepts. Okay, and let's think about what we've got here. We just found this one, check. T is temperature, we were given that. R, this is taking you way back. R is the gas constant. And you all, if you look at your equation sheet, you have 3 different possibilities for R. However, are you listening? You don't get a choice here of which one to use. If you look at your equation sheet, guys, you will notice that the very first gas constant value that's listed, 8.314, has units of joules in it. So that is the one to use with thermodynamic calculation. So I have this. So this equilibrium constant must be my unknown. Okay, fine. Well, before I start plugging numbers in, you have to be very careful about your units. Let me say again, the value for R that you need to use is 8.314, and look at its units. It's got joules. Well, I've got kilojoules here, so I can't mix kilojoules and joules into the same equation. So I'm going to turn this delta G value into joules before I do anything else. So let's see, that's 218,100 joules equals negative, plug in that gas constant. Temperature was 298 K. Okay, we do a little bit of algebra and we get down to this. And I have not rounded this number too much. Okay, now remember the way to sort of quote undo a natural log is to say e to the power of this number, and here's what I get for K. A very, very small number. Very small. Okay. Now, we're not quite finished with the problem, but I just want to pause for a moment and kind of bring some concepts together here, and then we'll finish the problem. Okay, direct your attention to the top of the screen where we solved for the delta G of the reaction, and it came out to be positive. What does that mean about this reaction? It means the forward reaction is not favored. Well, guys, look at the K value. I mean, K is, remember, products over reactants. And this number, this fraction, this ratio is really, really small. So that's kind of like rewriting products over reactants like little products over huge amount of reactants. So is this reaction going in the forward direction very much at all? No, it isn't. So you can tie these things together. When we say a reaction is not favored in the forward direction, we mean it. There's very little product being made here. Okay, now let's finish the question. We've got the K value, but it said, what is the equilibrium concentration for carbon dioxide? Guys, look at the reaction. Please pay attention to states of matter. When you write an equilibrium expression, what states of matter get included? Gases and aqueous only. Solids are excluded. So guess what? Here's my equilibrium expression. That's it. It's the only thing that gets included. So the K value is equal to the molarity of CO2. I'll round it a little bit though and put some units on it like a good science student. Okay, but that is a very, very small concentration, and it should be because this reaction is not going to be producing much product at all. Okay, so we're sort of bringing some concepts together here. So let me do that even further. Okay, let's think about the question we just did, where the delta G was very, very positive. The forward direction, the forward reaction is not favored. And look at the kinds of K values we get. They're incredibly small. Okay, they're not zero, and you can't ever have a negative K value, but they are between 0 and 1, which means reactants are favored. not products. Whereas, look at the other end. When delta G is very, very negative, the forward direction is favored, products are favored. We get very large K values, much greater than 1. Last but not least, if delta G equals 0, the K value will be exactly 1. The ratio between products and reactants will be equal to 1. Okay, if you don't believe me, you can plug in 0 into that equation, delta G equals negative RT ln K, you will get a value of 1 for K. So this is the last thing, and I know it's a lot. This is a big free response question. Okay, but I want you to pause the video and try all of these questions. It kind of brings together some of the topics we've talked about today and also some of our previous topics. So see how you do. All right, let's check each answer individually. Okay, we are given a decomposition reaction. N2O4 decomposes into 2 moles of NO2 gas. And the first question says, predict the sign of delta H. And if you look at the diagram, the way it's drawn, what's happening? We're breaking a bond. Well, anytime you are breaking bonds, it takes to break, remember? Remember that phrase? So delta H is going to be positive, endothermic, because energy must be absorbed when bonds are being broken, okay? Then it asks us to predict the sign of delta S, the change in entropy. Okay, again, look up to the reaction and ask yourself, is this process getting more organized or more disordered? Delta S is going to be positive. Think about states of matter and moles of states of matter. We have 1 mole of a gaseous reactant is being converted into 2 moles of gaseous products. Entropy is definitely increasing. So delta S is going to be positive. Okay. Then we are given 3 graphs. Temperature is on the X, delta G is on the Y. Okay, and I want to recall what we just said, that delta H is going to be positive and delta S is also positive. Think back a couple of subunits. We had a chart where we were given a whole bunch of, 4 different combinations of signage for delta H and delta S, and when are those combinations going to result in a favored reaction? If you go back and look at your notes, you'll see that when delta H and delta S are both positive, it says this process will be favored at high temperatures. Okay, and we talked about in that lesson, what does that mean? Quote, high temperatures. But if at higher temperatures, the reaction is becoming more favored, what does more favored mean in terms of delta G? More negative. So I'm hoping that you circled that graph as temperature. So I'll read what I said. With an endothermic delta H and a positive delta S, a reaction will become more thermodynamically favorable at higher temperatures. Thus, as T increases, delta G will decrease. Remember, a decreasing delta G means becoming more favorable. Okay. Part C, a reaction mixture of the same reaction we've been talking about. It's at equilibrium. Heat is added to the mixture while it is maintained at constant pressure. Explain why the concentration of N2O4 decreases. Okay, well guys, let me just remind you of something you said earlier. We said delta H, the change in enthalpy, was positive. That means it's endothermic. Okay, so think about it before I pull up the answer. Reactants, products. If it's endothermic, heat is treated like a reactant. So if we add more heat, that's going to cause the reaction to shift in the forward direction, creating more product and consuming some of the reactant. Well, guess what? N2O4 is a reactant. So let's see. So I said the reaction is endothermic. With an increase in heat, the reaction is driven to the right, which will produce more NO2, that's a product, and consuming N2O4, our reactant. That's why its concentration is decreasing. Okay. Next part says the value of the equilibrium constant at 25 degrees is 5 times 10 to the negative third. Will the equilibrium constant at 100 degrees be greater than, less than, or equal to this value? Okay, well, think back to what we said at an earlier part. At higher temperatures, this particular reaction will become more favorable in the forward direction. If that's the case, and it's going to be shifting to the forward direction, we're going to be creating more and more product. Product is in the numerator when you're calculating K. So the value of this new KEQ at 100 degrees will be greater. With an increase in temperature, there will be more product made. That's something we said in part 1, which will increase the equilibrium constant. Last part, using the value of K given in part C, part 2, just above us there, predict whether the value of delta H is expected to be greater than, less than, or equal to the value of T delta S. So they're basically asking us to think about this equation and compare this to that. How are we going to know which one is bigger? Because we're going to know this. Maybe not the exact number, but we'll be able to know whether it's positive or negative. Okay, so look up back at the question above it, right here. Okay, that K value is less than 1. If you think back to that chart a couple of slides back, when K values are less than 1, that's indicating a reaction that is not favored in the forward direction. Okay, so that means delta G must be positive. So since that K value is less than 1, that indicates a delta G that will be positive, and using that equation, a positive delta G indicates that that term delta H must be greater, larger than the other term, T delta S. So that is a good example of a multi-part free response question. That was a lot of conceptual thinking, and I know that that can be challenging sometime. But I hope that you learned a little something today, and I look forward to seeing you next time.